First, we need to install the WolkenShape plugin in Rhino. After downloading and extracting the WolkenShape installation package, open Rhino 8. In the main window, select Properties to open the Document Properties window. Then select Plugins on the left and click Install. In the File Selection dialog, navigate to the extracted plugin folder. Select the WolkenShape for Rhino.rhp file, and confirm. When opening the plugin toolbar for the first time, the system will ask you to set up the license. Please complete the license validation using the local or online verification method provided by us. Install the WolkenLasImport plugin in the same way. After installation, WolkenShape for Rhino and WolkenLasImport will appear in the plugin list. Next, I will introduce the steps for importing point clouds and setting their properties. Please note that subsequent algorithms can only run properly on point clouds that have been processed by Yunzi semantic segmentation. The point cloud is imported into Rhino as a referenced file, rather than being embedded in the Rhino document. Therefore, please keep a local copy of the original point cloud file. Otherwise, the point cloud cannot be loaded again when the document is reopened. Click the Import Last button to open the File Selection dialog. Select the point cloud file you want to process and confirm the import. If the current document unit is not set to meters, the plugin will first prompt you to switch the unit to meters. Select the point cloud file you want to process and confirm the import. If the current document unit is not set to meters, the plugin will first prompt you to switch the unit to meters. The visible column controls the visibility of point clouds in each category. Clicking the visible header will select or deselect all categories. The visible column controls the visibility of point clouds in each category. Clicking the visible header will select or deselect all categories. Below the semantic category display area is the point cloud offset section. Here, you can apply an offset to the coordinates of the imported point cloud. If the point cloud uses a coordinate system such as CGCS2000, it may contain very large coordinate values. In this case, the plugin will attempt to offset the point cloud coordinates. If no point cloud has been imported into the document yet, the default behavior is to move the point cloud from the center of its bounding box to the origin. If the document already contains an imported point cloud, the system will use the offset value from the existing point cloud by default. Click Edit on the right to open a dialog with 3 offset options. Use offset from last file defined in the point cloud file. Move from bounding box center to origin moves the point cloud from the center of its bounding box in the global coordinate system to the origin. If another point cloud has already been imported into the document, use offset from another point cloud can be used to obtain the offset value from that existing point cloud. Below the offset toolbar is the point size slider. You can adjust this slider to change the displayed size of the point cloud points. If color point cloud by classification is enabled, the point cloud will be colored according to its semantic classes. If color point cloud by classification is enabled, the point cloud will be colored according to its semantic classes. You can also double-click the classification or color field of a category to customize its semantic name or display color. When both enable points snapping at the bottom of the WolkenShape plugin and point in Rhino's OSNAP panel are enabled, geometry drawn in Rhino will automatically snap to points in the point cloud. Next, I will introduce the Extract Planes function. After selecting the point cloud, click the Extract Planes button. A settings window will appear. You can hover over each parameter name to view its detailed description. The first parameter is KNN. This parameter indicates how many neighboring points the algorithm refers to when determining whether a location belongs to a plane. It mainly affects how the algorithm makes the judgment. In most cases, the default value is sufficient and does not need to be adjusted. Next is area threshold. Planes smaller than this area will be ignored. This parameter is mainly used to filter out planes that are too small or fragmented. Increasing the value produces cleaner results, while decreasing it preserves more small-scale structures. Next is rectangular output. This option determines the output format. When enabled, the extracted result will be organized as rectangles. When disabled, the result will remain as polygons that better match the original shape. In general, enable this option if you want cleaner and more regular results for downstream modeling. Disable it if you want the boundaries to follow the original point cloud more closely. If rectangular output is enabled, rectangle expansion distance becomes active. This parameter expands the generated rectangular boundary outward by a specified distance. It is useful when the point cloud edges are incomplete and you want the rectangle to extend slightly beyond the detected boundary. The next option is align rectangle horizontally. This option makes the orientation of the generated rectangles more regular. For example, due to missing data or noise, some extracted rectangles may appear slightly tilted. When this option is enabled, the system will try to align them more neatly. Please note that it only adjusts the rectangle's direction within the current plane, and does not change the tilt of the plane itself. Align angle threshold determines which planes are suitable for this type of orientation adjustment. You can think of it as an angular threshold. Based on this value, the system decides whether a plane should remain unchanged or be horizontally aligned. This function is more suitable for non-horizontal surfaces such as walls, doors, windows, and sloped roofs. Next is intersection check. When enabled, the system checks the relationships between different plane segments and tries to make their edges connect more naturally. For example, if two walls or a wall and a roof should theoretically meet, this function attempts to make the connection more continuous. If intersection check is enabled, the following parameters control how plane segments are connected. Minimum plane side length sets a minimum side length requirement, and can be understood as another filter for small plane segments. If a generated plane segment is too short, it will be removed, so that only more meaningful results are retained. Plane fitting distance threshold is the distance threshold used during plane fitting. It affects how the system fits a plane based on the point cloud. This is usually a lower-level parameter, and the default value is recommended in most cases. Vertex to intersection maximum distance is used to determine whether two plane segments should intersect. Simply put, if the vertex of one plane segment is already very close to the plane of another segment, the system will consider them connected and try to make the edge transition more continuous. Wall-to-roof distance is mainly used when both walls and roofs are involved in the extraction. It determines whether the top of a wall is close enough to the roof surface. If the distance is smaller than this threshold, the system will try to connect the wall and roof seamlessly. At the bottom, the classification list shows all semantic classes in the current point cloud. Only the selected classes will participate in the plane extraction. By default, roof, wall, canopy, and ceiling are usually selected. After setting the parameters, click OK to start extraction. Please note that plane extraction processes all selected categories in the current point cloud and is not affected by slicing or crop boxes. The result shown here is generated with rectangular output enabled. We recommend switching Rhino's display mode to ghosted or shaded to view the plane segments properly. You can enable display planes at the bottom of the tab to show or hide the generated plane segments. Click the Manage button on the right to open a window showing all plane segments generated from the point cloud. After the Manage window is opened, you can select any plane segment from the list or directly in the viewport. Hold Ctrl and click a plane segment to add it to or remove it from the selection set. Hold Shift and click to select a continuous range. Visible controls whether a plane segment is shown or hidden. Imported indicates whether the segment has been imported into Rhino. Classification shows the class of the segment. Area shows its area, and confidence shows its confidence score. Clicking the headers of classification, area, or confidence switches between ascending and descending sorting. Click Sort to open the Advanced Sorting Settings window. The left side displays all sorting conditions, which are applied in priority order from top to bottom. After selecting a condition, you can view and modify its name and sorting order on the right. The left side displays all sorting conditions, which are applied in priority order from top to bottom. After selecting a condition, you can view and modify its name and sorting order on the right. After selecting the desired plane segments, click Import to import them into Rhino. You can choose to import them into the current layer or create a new layer. If you choose to create a new layer, the system will create a layer named plane_classification for the corresponding class. Re-importing objects of the same class will not create duplicate layers. Imported plane segments will be marked in the Imported column of the Planes Management window. If an imported plane segment is deleted, the checkmark in the Imported column will be removed accordingly. If you select a plane segment that has already been imported and import it again, a prompt will appear informing you that the previously imported segment will be disconnected from the plugin. After clicking OK, the previously imported segment will no longer be managed by the plugin. From then on, clicking the list item or plane segment will only highlight the most recently imported version. Click Clear to remove the plane segments generated from the current point cloud. Plane segments that have already been imported into Rhino will not be affected. If needed, the plane segments can be generated again. Next, I will introduce the beam and column extraction function in WolkenShape. After selecting the point cloud, click the Extract Cylinders button to open the settings window. The parameters are explained as follows. First is KNN. This parameter indicates how many neighboring points the algorithm considers during clustering. It mainly affects how the algorithm evaluates the local point cloud. In most cases, the default value is sufficient. Max radius indicates the maximum allowed radius when extracting cylinders. You can think of it as an upper limit. If the detected result is too large and exceeds this range, the system will not match it as a normal cylinder. This parameter mainly limits the recognition size and prevents clearly unreasonable results from being included. Normal distance weight is the normal distance weight. It affects how much the algorithm relies on directional information when determining whether points belong to the same cylinder. This is a lower-level parameter, and the default value is usually recommended. Max iterations is the maximum number of iterations. A larger value allows the algorithm to spend more time repeatedly fitting the result, which can improve accuracy, but it will also significantly increase processing time. The default value is already balanced for speed and performance, so it usually does not need to be changed. Distance parameter is the initial distance threshold. It can be understood as the criterion used at the beginning of the process to determine whether a point is close to the target shape. Radius step is the increment used when gradually adjusting this threshold. Both parameters are internal fitting controls, and it is generally recommended to keep the default values at first. Next are several parameters that have a greater impact on clustering results. Cluster tolerance indicates the allowed average distance within the same point cluster. If the point cloud is dense, reducing this value may improve recognition accuracy. If the point cloud is sparse, it is generally not recommended to set this value too low, as this may split structures that should remain connected. Min cluster size is the minimum number of points required for a cluster to be treated as a valid target. If the point cloud is dense, and small fragments are often mistakenly identified as beams or columns, this value can be increased to filter out noise. Max cluster size limits the size of a single cluster and usually does not need to be adjusted. Min cylinder size indicates how many points a cylinder must contain in order to be retained. This parameter mainly affects the balance between missed detections and false detections. The next parameter, radius threshold, is especially important. When the detected radius is greater than this threshold, the target will no longer be output as a cylinder. Instead, it will be converted into a cuboid. In other words, this parameter determines whether the result is more likely to remain a cylinder or be converted into a cuboid after exceeding a certain size. Angle threshold is the angular threshold. When two nearby cylinders have an axis angle smaller than this value, the system will try to merge them into one cylinder. If the point cloud has significant missing areas and the same component is broken into several segments, this value can be increased to help the system merge them back together. Height ratio threshold is used when merging nearby cylinders. It compares the height ratios of different cylinders and determines whether the maximum radius should be updated during merging. This parameter mainly affects the size evaluation after merging, and can usually remain at the default value. The classification list at the bottom shows the semantic information of the current point cloud. Only selected classes will participate in the beam and column extraction. By default, beams and columns are usually selected. After setting the parameters, click OK to start extraction. Please note that beam and column extraction processes all selected categories in the current point cloud and is not affected by slicing or crop boxes. If you need to stop the process midway, you can click Abort. After the algorithm finishes running, the results will be inserted into the document as cylinders or cuboids. Next, I will introduce the rough building model generation function in WolkenShape. Select an outdoor point cloud with semantic segmentation information. Then click Generate Rough Model to open the settings window. The first parameter is downsample voxel size. This controls the level of detail used when downsampling the point cloud. A smaller value preserves more point cloud details and usually produces a more refined model. But it also increases computation time. A larger value improves processing speed but reduces detail. The default value is already balanced for speed and quality and usually does not need to be changed. Next is pixel size. This parameter defines the grid size used when calculating building height, and it directly affects how much detail is preserved in the rough model. A smaller value retains more roof and outline details, but it significantly increases computation. A larger value creates a more simplified model and runs faster. This value is usually between 0.15 and 0.3, and the default setting is generally recommended. Min point indicates the minimum number of points required for a single roof to be treated as a valid target for modeling. You can think of it as a filtering condition. Targets that are too small or fragmented will be ignored and will not generate separate models. Next is optimization timeout, which sets the maximum optimization time for a single building model. If a model takes too long to compute, the system will stop the current optimization and try to split it into smaller parts for remodeling. Lowering this value can reduce overall processing time, but it may cause a building that should remain complete to be split into more fragments. Increasing the value may produce a more complete result, but it will also take more time. Enable parallel computing controls whether multi-threaded computation is used. When enabled, the system can use multiple threads at the same time, which usually reduces total processing time significantly. However, in some cases it may be less stable. The next group is algorithm lambda settings. These three parameters mainly determine the final tendency of the rough model. They are not independent from one another, and their total is limited to 1. Therefore, when one value is increased, the influence of the other two is reduced. In general, the default values provide a good balance, and we do not recommend changing them without a specific need. The first parameter is data fitting. It determines how closely the generated result fits the original point cloud. A higher value makes the rough model follow the point cloud more closely, while a lower value makes the model more regularized and simplified. The second parameter is model height. It mainly affects how roof height is processed. For example, when the roof point cloud contains multiple layers, such as a translucent roof or stacked roof structure, this parameter determines whether the result tends to keep only the topmost roof surface. The third parameter is model complexity. It determines the complexity of the final rough model. A higher value may preserve more shape variations and roof details, while a lower value produces a simpler and more regular result. After setting the parameters, click OK to start generating the rough building model. Next, I will introduce the point cloud slicing function in WolkenShape. After switching to the point cloud slicing tab, click Add Slicing to create a new slice. Users can choose either horizontal slicing or vertical slicing as needed. For horizontal slicing, select a point in the front view or side view of the point cloud. After the cutting position is selected, a dialog will appear for slice settings. The first setting is slice thickness. You can adjust the thickness until the building outline on the slice becomes clear. Create slicing across multiple point clouds controls whether the slice is applied to multiple point clouds. When enabled, you can select the point clouds to which the slice should be applied from the list below. After the slice is created, you can drag the cutting line with the left mouse button to change the slice position. You can also create a vertical slice by selecting 2 points in the top view of the point cloud. The vertical plane formed by these 2 points will be used as the slicing plane. Alternatively, you can first create a horizontal or vertical slice, then use Edit Slicing to adjust the tilt angle of the plane and create slices at other angles. After a slice is created, it can be turned on or off in the toolbar below. You can double-click to modify its name, color, thickness, and other properties. You can also use Edit Slicing to modify the slice name, thickness, starting point coordinates, plane tilt angle, line tilt angle, and the point clouds to which the slice should be applied. Next is the Extract Borders function. After clicking Extract Borders, you need to select an extraction method in the dialog. The 2 available methods are extracting borders from previously extracted planes, or extracting borders directly from the sliced point cloud. Extracting borders directly from the sliced point cloud can produce more accurate results, but it is not suitable for point clouds with heavy noise. The parameters of this function are explained below. First is downsample voxel size. This parameter controls whether the point cloud should be made sparser before processing. A larger value makes the point cloud more sparse and improves processing speed, but it may also reduce the probability of successfully extracting border lines. In most cases, the default value is recommended. Next is line detection sensitivity. This parameter determines how sensitive the algorithm is to small changes. A smaller value makes the algorithm more sensitive, while a larger value makes it more stable. If many large wall sections are not extracted, you can reduce this value. If the result contains many fragmented or noisy line segments, you can increase it. Next is max wall deviation. You can understand it as the algorithm's tolerance for walls that are not perfectly flat. A larger value makes the system more tolerant of irregular or noisy point clouds, but it may also mistakenly identify objects as wall lines when they should not be. A smaller value makes the judgment stricter, but it may miss some real wall lines that are not perfectly regular. For example, if the same wall is extracted into several parallel lines due to noise, you can increase this value. If one of 2 very close parallel walls is not extracted well, you can reduce it. Next is max corner gap, which is the threshold for connecting corners. It mainly handles cases where 2 line segments do not fully meet at a wall corner. Simply put, if the distance between the endpoints of 2 line segments is smaller than this value, the software will try to extend them and connect them to the same corner point. This parameter is useful when wall corners are not closed or when corners are broken. If some wall corners are not connected, you can increase this value. However, if it is set too high, corners that should not be connected may be incorrectly joined. Next is max collinear gap, which is the maximum gap allowed between collinear line segments. This parameter mainly handles cases where a line should be continuous, but has a small gap in the middle. A larger value makes the software more willing to connect line segments that have gaps but still lie on the same line, while a smaller value makes the connection more conservative. A larger value makes the software more willing to connect line segments that have gaps but still lie on the same line, while a smaller value makes the connection more conservative. However, if the value is set too high, elements that should not be connected may also be joined incorrectly. The last option is Don't read original point cloud file. When this option is enabled, the algorithm will not read the original point cloud file again. Instead, it will use the point cloud currently loaded in Rhino. This can significantly reduce processing time for large point clouds, but the extraction quality may decrease. If speed is the priority, you may consider enabling it. If quality is more important, we recommend leaving it disabled. After border extraction, you can use the connect line segments function to connect fragmented line segments from extract borders into more complete polylines. Next, I will introduce the crop box functions in WolkenShape. In the Crop Box tab, click the plus button to create a new crop box. In the top view, select a rectangular region on the horizontal plane to define the crop box position. If multiple point clouds have been imported, a settings window will appear, allowing you to select which point clouds the crop box should be applied to. Edit crop box is used to edit the crop box. Here you can modify the center coordinates of the crop box, its dimensions in 3 directions, and its rotation angle. Preview allows you to view the effect of the modified parameters in real time. You can also create point cloud slices within a crop box. Slices created inside a crop box will be shown in the crop box column of the slicing list and in the slicing column of the crop box list. After slices have been created inside a crop box, deleting the crop box will trigger a prompt indicating that the slices created within that crop box will also be deleted. Finally, I will introduce the functions in the settings section. The first option is Set C-plane to Active Slicing Plane. When this option is enabled, the construction plane will be set to the plane of the current point cloud slice when the active tab is switched to slicing. When subsample large point cloud using octree is enabled, large point clouds will be uniformly downsampled using an octree during import. If it is not enabled, large point clouds will be randomly downsampled instead. When Show Refresh button in toolbar is enabled, a refresh button will appear at the top of each tab. When Always Highlight Slicing is not enabled, slices of the current point cloud will only be highlighted when the slicing tab is active. When this option is enabled, point cloud slices will always remain highlighted.